Hello, everyone. So today we are going to discuss the mathematical evidence of decision tree. Like we have already discussed the concept of decision tree. And like I mentioned, it is not a very efficient algorithm to use for the machine learning problems in the real world scenario because of the limitation in you. We're gonna see that it is not performing efficiently against the big data sets or medium data sets. But the best part of decision tree, it is going to be used for our next algorithm, which is obviously the a random forest, which has been used a lot into the classification problem into the industry. So and that's why the understanding of decision tree is important, that if you understand it correctly, you're going to have a very good grip on the random forest. And like I mentioned, we're going to see it in action very soon, once we run the random forest to our PySpark notebook. So let's coming back towards the mathematical evidence. Like you can see, the whole concept has been based upon the information entropy or information gain concept there, which means that how much information you can get once you start dividing the data elements between nodes. So the very first concept, let's see, before we start proving the equation, is the information entropy. And it is more likely the smallest piece of data that can be used to represent the information. Sometimes if you want to represent, for example, for option, we normally use 2 bits, right? 2 bits is enough for us, instead of, if we allocate a full byte, and that's where the whole concept of byte, kilobyte, megabyte comes into the picture to represent the information. And you can go deeper if you have interest to see how the binary works once we start, representing different option. So the formula is pretty simple. Like it is the probability of the outcome multiplied by the binary log of the probability of the outcome, and then it continues. It has the minus sign all the way till the nth outcome of the sample space. All right, and the sample space is more like we normally because we are talking about probability, so instead of sample space, we're going to actually call it probability space of and we're going to represent is as with the element obviously 1 to n. Now let's take a small example to see if we toss a coin which has two faces, the head and tail. So let's calculate the information entropy for this coin. And obviously, like you can see, we represent the outcome with s. We only have two outcome, right? Head and tail. So you can see the outcome. The first outcome is going to be 1 out of 2. So the probability would be 0.5. And obviously, we are getting the log or log 2 of 0.5. And the same thing is with the other outcome, because the other outcome is tail. And that is also going to be the similar probability, which is 0.5 multiplied by log 2, 0.5. And then they constitute equal to, if you can actually calculate the log, it's going to be a positive sign. It's going to change the sign, because log 2 is equal to log 2 of 0.5 is going to be -1. In different calculator, it provide us different value, but that all round of if you round the value, it's going to be -1, and -1 multiplied by 0.5 is going to give you 0.5. So you can see the total information entropy of the full probability space is going to be equal to 1. So that's the main ingredient that we need to know if we want to understand the mathematical evaluation of the decision tree. Now, the very next thing, which is the main contributor that actually use, because It is easy for us. Let's take this way. It is easy for us to construct the tree. We have bunch of data. We can start with any variable. We can, start putting the values of that variable, and then underneath we can start creating the branches. But that's not a very efficient way to construct a tree, right? Because we need to find the best way that where we can, efficiently distribute the information. Otherwise, our tree is going to be very bushy. Like, it has so many branches which are, just staying there without contributing into the efficiency. And obviously, the computationally, it's going to be very expensive to, to find the right outcome. So that's where the whole information entropy comes into the picture. Now, the second one, which we use to decide, okay, which variable we are going to use to start constructing and then splitting our tree at the later level, that is called information gain. And information gain is the amount of information entropy as a result of certain procedure, and we normally calculate it by using following formula. It is obviously, we have already calculated the information entropy for the full probability space, and then we use the variable which we are interested to calculate the information gain for. We use the value length of it, and then we divide by the total number of values, and obviously we calculate the information entropy for that particular value of the variable. We're going to discuss it in the upcoming example, because theoretically it's going to be difficult to understand. All right. So let's take a small scenario where we are deciding to a swim preference situation. So we have only two variables for simplicity. We have swimming suit and we have water temperature. Obviously, we don't have swimming suit. Regardless of the water temperature, we are not going to swim. That's our preference. But if our swimming suit is small and the water temperature is cold, we are not going to swim. Similar, if the water temperature is going to be warm, but we don't have a proper swimming suit, we are not going to swim. Now, the last condition, the swimming suit is good, but the water temperature is cold. Our preference to stay away from the water. We don't want to get sick. However, if we have a good swimming suit and we have the water temperature normal fuzzy that we can enjoy, so our preference is that we are going to swim, right? So that's a small outcome set, and based on that we are going to design the decision tree. Now you can see by looking at it, we have two independent variables, swimming suit and water temperature, and we have one target variable which is swimming preference, right? Which has only two outcomes. So it's more like the binary classification problem set. Now let's calculate the information gain for our first variable, which is swimming suit, and you can see we are going to substitute value into this formula to get the information gain. Now, the very first thing, let's define the number of pairs based on the unique value of the variable. So we have 3 unique value. So that's why our probability space or the set is going to be the number of sets are going to be 3, and each set, like we can see, each set has two outcome. So we just put the member of the set is the values of the set which is inside of the set, right? So obviously for none we have a combination of none, cold, no, none, warm, no. And you can see if we have large number of variables and we have large number of values, it's not going to be very efficient to run against the computer, which has limited, I would say, power to calculate the information gain, right? So keep that in mind. That's why it's not very practical algorithm that we use day-to-day basis. All right, so we have S none, similar terms, we have S of small, and then we have the set of good, and each is containing its respective rows. Now, how we are going to calculate the entropy? Entropy obviously is going to be the outcome, probability outcome divided multiplied by the log for all the values. But here you can see we only have one outcome, which is no. So log of 1 is always going to be 0. So regardless whatever value is going to be the outside, we can safely put the entropy is going to be 0 in this case. Similar way with the small one, because small also have the similar outcome, so that is also going to be 0. Now the only remaining one is the good, the swimming suit having the value of good. It has two outcome. With cold and no, it's sorry, with cold it's going to give us no, and with warm is going to give us yes. So now based on that, obviously we are going to have one outcome out of two. So you can see the probability value is going to be 1/2, and obviously we are going to take the log of 1/2. The similar way of the other outcome, and we have already seen this in the example of coin toss, right? So the total entropy is going to come to us as 1, right? So we have all the entropies for all the values of swimsuit. Now what we are going to do, we are going to calculate the total entropy for the full set. So if you can look at it, we have one outcome out of 6, which is yes, and then we have 5 outcome out of 6, which is 5, right? So that's the total outcome of the full set. So what we are going to do, I was just thinking that I put it in the reverse order. Theoretically, because we are treating no first, so no should come first. But anyway, sequence doesn't matter, because the sign is not going, sign is all same, and it will give you the same value if you actually put it the other way around. All right, so minus 1/6 log 2 of 1/6, the same formula, and my 5/6 for no value, the first one for yes value, and you can, if you calculate it, it's going to end up 0.065002. Now we have all the value of this equation. We have the entropy of our total probability set, or we have the value of entropy value of all the value of S of swimming suit, right? So that's where it is different. S of V is different from S. Now we are considering it in the context of the variable. So now what we are going to do, we are just going to now start putting the value. We are going to calculate the information gain of swimming suit. So we have two values for none out of 6, because if you can see in here, we have 6 rows, and out of 6 we have 2. So that's the length of the SV for our first set, which is S of none. The second one is same, S of small, and the third one is same of S of good. And entropy of S of none, we calculated 0. The entropy of S of none, S of small is 0 as well. The entropy is, however, the S of good entropy is going to be 1. So if you calculate all the values, you're gonna end up in 0.65002242 minus 1/3, and if you divide 1/3 and get the value to subtract it 0.65, we're going to end up 0.316889. That's the process to calculate the information gain of one variable, right? So we have calculated it for swimming suit. Now on the similar lines, we can calculate these information gain for water temperature, which you can do by yourself if you are interested, and that's going to be 0.190874. Now we always start the tree with the maximum information gain, which is in this case is going to be our swimming suit, because that's the variable which is giving us the maximum gain on the information. So you can see if we construct that tree, because once we put the first variable, the second variable is more like, we don't need the second variable in here on the second level, because we don't have multiple outcome, we only have one outcome. So you can see we have tree ended in the second node in here against none. Tree end up in the second node on the small node as well. However, on good, Now we need to construct another branch, which is obviously based on the water, because we only have one variable left. If we have more variable, we're going to recurse it as long as we have all the variables has been sorted out. And based on the water, we have cold and we have warm. So you can see a very nice small tree, but that will give you a full understanding how you can construct the Gaussian tree for the given data set. Now keep in mind, for the real life scenario, the equation, the mathematics remain exactly the same. It's more like you add more and more complexity and more data points or more and more attributes in your data to calculate the outcome from your decision tree.